I know, I always make good points.
How did she get 9 minutes? I don't know.
Where, do you want her to know about this too?
Do it. Our class.
I love those videos online where it's like a guy's like
Soy boy struck again. He
he
drew the thing on right. He drew like a tombstone.
Oh man.
Oh no.
Soy boy?
I don't know if that means he's giving it up or whatever, but. So we're going to continue with related rates. It's a word problem. Well, it's a kind of, they will usually appear as word problems on your test. How do you know it's related rates? Let me turn this around a second.
As something occurs, something else occurs.
As something occurs, something else occurs. That's very vague.
That's like
The rates are given to the rate.
So you're given related quantities. Right, so you're told about quantities that are related in some intimate way. And yeah, as you said, you're given rates. So someone's going to tell you there's something that's increasing by this much, or there's something that's decreasing by this much, or there's something that's the rate of change is this, right? And you're asked to find another rate. That's of course related to the first rate. Hence the name related rates. So the thing is, the idea is when quantities are related by some equation, their rates are automatically also related by an equation by just differentiating that first equation. And so we can talk about the rates of one thing when we know about the rates of the other thing. And once we know that this is the situation, we find ourselves in this, there was a 6-step process in order to do any related rates problem, right? So we have a 6-step process to solve these. Too bad Alex wasn't here last time, because I think you said related rates was something that's tough for you. Did you say that? Related rates?
I think 2 classes ago.
Yeah, something like that. So where we talk about related rates versus optimization, like this one is the harder one. I don't necessarily agree. We're going to do both, and then we can compare. But related rates we had, so you weren't here. So did you get the handout?
No.
Do I have extra?
Yes.
No. Well, you can get the handout from the class website. Okay, so that was the idea. That's what we talked about last time. We actually did 3 examples, so what we're going to do is we're just going to move on to example 4 in the handout, which you can pull up from the class webpage if you didn't do it. And we'll just review the 6 steps while we're doing this. So like I said, we're going to do up to example 6. Example 7 through 11 is kind of stuff you can try on your own if you want, like more bonus problems, points, or something similar. So let's start with problem 4. The volume of a sphere is increasing at a rate of 5 cubic feet per second. How fast is its radius increasing when the radius is 2 feet in length? The volume of a sphere of radius r is given by v equals 4/3 pi r cubed. So, step 1. Read. Very important. Read the problem, right? Because 1, you need to figure out, first of all, it's a related rates problem, and we know that this is a related rates problem because it mentions about how the volume is increasing at this rate and blah, 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 and you're asked to find another rate. So we know it's a related rates problem, and we need to pick out the important information. What was the second step?
Draw a diagram.
Right, draw a diagram that represents the situation. And in the fine print, or the regular font, not the bold font, we kind of said that the point of this was for you to have ideas about the kind of formula you want to set up, right? So it turns out here, I would skip this step. It's not necessary. Why? Because when I read the problem, I realized that the formula was actually given. So I don't need a picture. I know what the relationship is already. They told us. 3, what's the third step?
What you know.
Right. Just list all the things we know and all the things you want to find. Well, what do we know so far?
dV over dt.
Right. We know the rate of change of volume
It's 5.
is 5. And again, just to remind you, it's positive since increasing. Right? If they told you that the volume was decreasing, like you're compressing the sphere, you would actually put a negative 5. And what do we want to find?
dr over dt.
Yeah, how fast is its radius increasing when the radius is 2 feet in length? So we want dr dt when
R is equal to 2.
So what's step 4?
Equation.
You come up with the equation. Now usually, step 2 would help us come up with the equation we want to use in step 4, but here the equation was actually given to us. So that was v equals 4/3 pi r cubed. So that's step 4 to come with that equation. Step 5, at this point you differentiate implicitly. Derivative of v.
dv over dt.
Derivative of that.
Oh.
Yeah.
Is it 4 pi r squared dr dt?
Right. So you have to remember it's implicit differentiation, which means that t is your independent variable. So if you're differentiating any other variable that's not t, you have to multiply by its derivative, right? Because the chain rule takes effect. So finally, we're at the 6th step. Which is?
Plug in and solve.
Right, you plug in and solve for what you want. So the 6th step is to just plug in. So dv dt we actually know. That's 5. 4 pi r squared. R we know is 2. And dr dt we don't know. It's actually what we want to find. So that means that 5 is equal to, that's 16 pi. So what's dr dt?
5 over 8 pi. What is it?
16. Yeah.
16 pi.
5 divided by 16 pi. And that's in cubic feet per second. So that's feet per second. Like I said, the units I don't really care about, so as long as you get 5 over 16 pi. And that's it. So again, you always go through these 6 steps to solve any related rates problem. First read, figure out that it's a related rates, glean the important information. You'd usually draw a diagram to set up the problem, especially if you're not given any relationship outright. Sometimes drawing a picture can jog your memory. So you know if it's a triangle, you know a bunch of formulas about triangles that you can use, and etc. Write on what you know, what you want to find. It's nice to have all this information written down so that when you get to step 6, it's easy to just pick them off and plug them in. You come up with an equation. If it's not given to you, step 2 is going to help you with that. And then you differentiate with respect to time and plug in, right? And we also saw the situations where if in step 6 you don't have all the information to plug in everything, you would go, what would you do? Suppose we got here and there was another variable that I didn't know the value.
Solve for it from
Right, you go back to step 4, you solve for the guy, and then you come back here, right? Because that relationship tells you what all the variables are doing. Okay, great. Questions?
You want any Skittles?
Hmm?
Does anybody here want Skittles? I don't want to finish this pack.
Just not the.
So I'm not resting.
I'll take the rest, what you don't want.
Okay. So let's do example 5. Example 5 has 2 parts. There's a part A and a part B. Slightly different. Okay, the side length of a cube is increasing at a rate of 2 inches per minute. when the side length is 3 inches, A, how fast is the surface area changing, and B, how fast is the volume changing. These are two very different problems, so we'll do them one at a time. So in part A, we care about surface area. So let's actually do that. What's step 1 here? Read. 2. Diagram. So what's the diagram here?
The cube.
It's a cube, right? So it's just a box. Okay. So you draw and label your diagram, and let's revisit how do we label things? What's the principle when we're labeling something? Like, how would you label this cube? So as the length of the cube is increased at the rate of 2 inches per minute, when the side length is 3, how fast is the surface area changing?
Do you just pick one line and
Label it as what?
as the side length?
Okay, tell me
Oh,
what
so like that, the one right here.
do you want to label it?
S.
S?
Yeah, side.
Well, you can mix that up with a 5 easily. Let's
Like
call it
L.
X.
Oh, X.
Okay.
Okay, and then what is this?
Y.
What is this?
Me.
Huh?
I don't know.
Is that
Yeah.
Whoa, whoa, whoa,
Wait,
whoa.
can't you just make it all X?
See, it's not
Can you just make it all
normal.
X because it's a cube and everything's the same anyway?
Okay, so yeah, labeling X, Y, Z is not, it wouldn't be very efficient. Technically it's not wrong, but you'd get into a lot of trouble because now you realize if you start to plug all these guys in, you'd have like a dy dt and a dz dt and a dx dt, and you're like, there's so many variables, don't make your life harder than it actually is. We know it's a cube, which means that all the sides have to be the same length. And so that's how we label it. So it's important that you read, right? Reading would have told you that it's a cube, so once you label one side, you automatically know the length of all the other sides. It's also possible for me to have described a box that says, oh, the length is twice the width, or something similar, in which case you'd put 2x here or something like that. Right? So it's very important that your labeling must make sense with the problem, and the main principle is anything that is changing, you label it with a variable, anything that is not changing, you label it with a constant, again to avoid confusion. Right? So here I will label these, the side lengths, with variables because they are changing according to the problem, and it turns out because it's a cube, all the side lengths are the same. So I would label it, all of them being the same. Okay. So there's the potential for a lot of confusion if you mislabel a diagram, and so you want to be careful about that. Step 3, we're going to write down everything we know and what we want to find. So what do we know?
dx over dt is 2.
So the side length is increasing at a rate of 2, so it's a positive 2. Okay. What else? What do we? Is that all we know?
X.
Yes. What do we want?
We want the surface area, right?
Okay. The rate of change of surface area. So we want dA dt when x equals 2. Was it?
2. 3.
3. Where A here I'm setting to be surface area. So now 4. What's the fourth step?
Equation.
Come with an equation. Right, so in your picture, you've just drawn the picture of a box. How do you find the surface area of a box?
6x squared.
6x squared. And this is basically the sum of the areas of all the faces. It's called the surface area. Right? So you just want the area of all the faces on the outside, but each face is going to be a square of side x. So the area, this is x times x, which is x squared, but that happens 6 times because there's 6 faces, and so that is the appropriate formula to write down here. Fifth,
Differentiate.
we're going to differentiate. With respect to time, so derivative of a,
dA over dt equals 12x dx over dt.
Which leads us to 6. Which is?
Plug in and solve.
Plug in to solve. So now dA dt, do we know that? No, that's what we want to find, so that's just dA dt equals 12 times x, which we know is 3, times dx dt, which we know is 2. So what's that?
72.
And let's see, it's inches per minute. So technically this is in squared per minute, but 72 is. So read diagram, right? I want you know what you want. Find an equation set up based on these variables and this picture. Differentiate that equation, plug in all the values, and solve for what you need. All related rates problems will go through this process. And again, as in the first example we did today, we can skip over certain steps, but we keep in general going in the same order. So if one step isn't necessary, just move on to the next step. And the point of doing this is to figure that out. So if they gave you an equation, you don't really need a picture anymore. But the picture is really there to help you visualize how you would set up the formula. So you visualize here that, oh, there are 6 sides to this thing that I just drew, and I want the area of each side. Each side happens to be a square, and you can come up with this formula. Okay, let's move on to B. So in problem 5, it's still describing a cube, so we already read, it's the same diagram. It's the same thing that we know, but what we want is different, right? So all of these are going to be different. Okay, so I have a cube whose side length is increasing at a rate of 2. What do we want to find here in part B? How fast is the volume changing?
Yeah.
So we need dV dt when it tells us when the side length is 3. So when x equals 3, where I'm describing V to be my volume. Equation?
B equals x squared.
V equals what?
X squared. Wait, no, V, x cubed.
X cubed, right? Because it's a box, the area of the volume of a box is length times width times height. So it's x times x times x, so it's actually x cubed. Next we're going to differentiate this. dV dt equals this.
3x squared dx over dt.
6, we're going to plug in. dV dt we don't know, that stays. But I know that x is 3 and dx dt is 2. And so what's that? Yes, that's 54. That reminds me of a joke. You guys ever see this one?
Yeah, I completely forgot how long it was.
I was like,
I haven't done long
It was-
division since middle school.
But yeah, someone asks you to do a long division, but like,
That's
you're
how
here
we-
doing calculus, differentiating, all sorts of stuff. Oh yeah, chain rule, quotient rule. Oh yeah, what's 3 times 3 squared times 2? Oh god, take my calculator.
That's
How do you
why
calculate
we
the
have
tip?
calculators.
Can't take it. Like I just have derivatives swirling in my head. Forget arithmetic. I think that was an XKCD comic.
When I was at home, I'd always get my 12-year-old little brother to do all my simple math for me.
Yeah. Come here, minion.
Like, you're not joking about, that's actually what I called him.
That's what I asked you guys about. I was gonna do that myself. So what's that? No. Okay, make sure you're paying attention. Okay. Example 6. The last one. Rate of the circle is increasing at a rate of 1 meter per minute. What is the instantaneous rate of change of the area of the circle? The instant the area is 4 pi. So 1, read. 2, diagram. 3, something in which you would define your variables as well as hopefully jog your memory as to what kind of formulas would apply to the kind of shape you're drawing. 3. So I have a circle, radius r, so that's my diagram. It's asking me about the area of the circle. I've defined A to be the area. So what do I know? What do I want? The radius of the circle is increasing at a rate of 1 meter per second. So I know dr dt is positive 1. We want the rate of change of the area. So we want dA dt when A equals 4 pi. So we want to set 4, we're going to set up an equation. So what equation would go with this?
A equals to pi r squared.
A equals pi r squared. 5, you're going to differentiate.
dA over dt is to 2 pi r's d. Yeah, r over dt.
And then finally 6, we're going to want to plug in. So what would we plug in here? Do we know dA dt? No. That's what we want to find. Do we know r?
No.
No.
You could solve it from there.
We don't know r. So we realize here we need to find r. And so the idea is go to back to step 4 to find r. So we know that a is equal to pi r squared. I know my a value is 4 pi. So 4 pi is equal to pi r squared. Divide both sides by pi, you get r squared is equal to 4, so your r is actually 2. It's not plus or minus because r is the length, so it's going to be a positive 2. And so now we can plug in dA dt is equal to 2 pi times 2 times dr dt. So it's also increasing at 4 pi in squared per minute. Yeah, where it says area is 4 pi cubic meters, that should be square meters. Area is square units. So that's the answer, 4 pi. That's basically it. Any questions on this labor rates. I think we kind of hammered it home that it's always the same 6 processes. So it's like a template that you're just going through and you're filling in. The hardest part really is if you need to come up with a diagram and label it properly to come up with the equation. But the rest of it is following your nose. And if the equation is given to you, then it's even easier. You don't have to even figure out a diagram. So, yeah, that does it. We're not going to do it. I only did 6 examples, but you can try the others as well if you want. Some more practical uses. I mean, here we're talking about circles and rectangles. Like, who cares? But there are some practical uses for things like these. I think 7, 8, and 9 kind of talks about some of those issues. Perhaps not applicable to everyone, but more applicable than what's the area volume of this cube? Whoever has to do that. So I also printed out. I won't get to this today, but just I printed it so you guys have to. So we should get to this on Friday. How many? Yeah, so this is a curve sketching handout because there are, again, a method to the madness when it comes to curve sketching. We won't do that today, but we will be doing something today that's important to being able to do the steps described there. In particular, things like the first derivative test, the second derivative test, how to find maximums and minimums. We're going to apply that to our derivatives. Yeah, so this is 4.2. Won't complete it, but let's start. This is called maximum and minimum values. There are going to be 2 kinds of maximums and minimums we care about, 2 main categories of these things. So let's just talk about them in the definition. So f of x be a function on an interval AB. We say f has an absolute. Another word you might see is global maximum. Or you say attains a global maximum at x equals x naught if at that point the function is greater than or equal to all other y values in that interval. So locate the point with the biggest y value on that entire interval, and that value is called the absolute maximum, or the global maximum. I'll illustrate with some pictures pretty soon, but that's. So if its y value is less than or equal to all other y values, then it's called an absolute minimum. So I have two similar definitions to tell you, and then I'll illustrate the difference between them. You write those down. So again, a set of two similar definitions. That's one type of maximum minimum. I'm going to describe the other type. We say f has a local or relative So local or relative, it's not talking about on the global scale, not talking about for all x in the interval, but just all x in some local neighborhood around the point that you care about. So if it's the biggest guy in his small little world, he's called a local maximum. Similarly, if he's the smallest guy in his little world, then he's the relative. That's local. So I'm going to illustrate the difference between them for you. Illustrations. Let's make sure we understand what those definitions are saying. So here's an example of a function that's with A, it's with B. So I just want you to locate in principle where the absolute and relative maximums and minimums are. So this is not official notation or anything, but it's just shorthand because I don't want to have to write it down. So let's say big M is absolute max. Small m is absolute min. Upper LM is local max. Lower LM is local min. Okay, identify these points just by like pointing on the picture. Let's deal with the absolutes first. Can you identify an absolute max on this picture? Yeah?
The top hump there.
The biggest hump, right? This guy right here, that guy's an M. He's an absolute max. If I look globally on the global scale, look at everything all at once, who's the biggest guy? It's that guy. That's called the absolute maximum. Is there an absolute minimum?
Lowest dip.
The lowest dip right here. So that guy here is going to be an absolute minimum, small m. Let's talk about local maximums and minimums. Can you identify it? Local maximums.
Right there. That one. Yeah.
This is a hump here, so that's a local maximum. Anywhere else? Yeah?
Would be point B.
At B, this
Yeah.
is also a local maximum, right? Because
So definitely.
so the difference between local is this and this were the biggest guys in general, but over here, notice that if I zoom in, I don't care about the entire picture, but in a small window around this guy, he's the biggest point, right? Notice that this is also a local maximum, right? He's the biggest guy in general, but also in the case that I zoom in, he's also a local maximum.
Could you have? I mean, you could have local maximums and minimums like all along it, right? Depending on where you zoom in. Like there could be points like along the whole graph that are higher or lower than others, right?
Yeah.
So it doesn't have what I'm saying. Like it doesn't have to be a point like on a change of like a hump or a valley.
Well, it could, we'll get to other illustrations later, but technically it doesn't have to be. This here is going to be a local minimum, right? This here is also a local minimum. This here, how do we identify this guy? Local minimum, because if I zoom in, all points close to it are higher than it. Around this guy. What's the absolute maximum?
Wait,
Yeah.
I have a question. Why
Yes.
would that one also be a local minimum? It's already absolute.
This one?
Yeah.
You can be both, because it fits the definition of both. It's both the smallest point in general, but also if you zoom in, it is also the smallest point. Right, absolute maximums and minimums happen to also be local maximums and minimums, but it's not true the other way around. The absolute is more like the big picture guy. Okay. What about this one? Absolute max. There's no absolute max here. Right? There's no point that I can pick that is bigger than everyone in general, because the graph keeps going up to infinity. Right? Any point you pick, there will be a point that's larger than it. Any absolute minimums? At A and B, we have absolute minimums. By the way, they're also local minimums. Right? If I zoom in on their region, they're also the smallest guy. So they're also local minimums. So this is a case where you don't have to have all these kinds of things present. What about this one? Absolute maximum?
No.
Any locals?
No.
No.
This one has none. Right? There's no M, LM, or LN. No maximums and minimums on this function. This one. Well, I think it's clear here that at the top of a hill is always going to be at least a local maximum. So here this is a local max, The depth of a valley is always going to be a local min. This is going to be a local min. Here this is the absolute min and a local min. Here, this is a local min. Is this point anything?
No,
Why not?
it's not filled.
Because there was a space income, so it's a space.
Right, so it's not even a point to consider. But what about this point?
It's absolute max.
Yeah, he's higher than everyone, so that's the absolute maximum. And this guy, notice that even if this were filled in, well, it wouldn't be a function if it was, but even if it were filled in, we'd still have a problem because neither definition would fit. Because to the left of him, there are points higher, but to the right, there are points lower. So there are a bunch of reasons why that guy's like nothing. And so, what about this one?
Would that also be a local max too?
This one?
Yeah.
Yes, because if I zoom in, if I look a little to the left or a little to the right, he's still higher than everyone. He's higher than all points on here. He's also higher than all points over here.
So are absolute max and absolute min always also going to be local max and min?
Yes, but not the other way around,
Not
of
that
course.
way.
Absolute max? Right at the top. Absolute min? No absolute min. Local max? This is also local max. Local min? No local min.
Wait, so you can still like have an absolute max even if there's no point on the because there wasn't a point there, you just made one. You made it
Well, it's going to be a point, right? This is the graph of a function. So how we get that graph is we're plotting a bunch of points anywhere, right? The point that is at the very peak is going to be that point. Right now, if your function is representing something that you care about, the peaks and the valleys are normally going to be important things for you, right? So if you can imagine that we're trying to measure something like profit, you want to make it the highest possible point it wants to be, and you want to avoid the lowest possible points. There are going to be reasons why we care about maximums and minimums.
So is there no
Yeah.
minimum because there's no dip and it just keeps going down?
There's no minimum because no matter what point I pick, there's always a smaller point. It keeps going down forever. So there's no smallest point, neither in general nor locally. Okay, so that's kind of the idea. So the absolute maximum and absolute minimum, they're talking about looking at the big picture. Who's the biggest guy? Who's the smallest guy? Local just means you're zooming in on hills and valleys and trying to identify them, right? Now there are some important theorems here. There are many important theorems. At this point, it's sort of where calculus starts to get interesting, but in applied calculus it doesn't, because we're going to skip a lot of the important theorems, and we're only really going to just mention some other kind of important theorems. One is called the extreme value theorem. It says if f is continuous on AB, then f is guaranteed. To attain its absolute max and absolute min on AB. In other words, if you're continuous on a closed interval, the absolute max and min has to exist. If you look back at all the other illustrations, in the cases where I said there's no absolute max or min, the problem was the function wasn't continuous on AB. Turns out that once you're continuous on AB, an absolute max and min has to exist. So you know it's there, you just need to find it. So that kind of just tells you when you know one will exist. As long as we're continuous, there's definitely one somewhere. It's either going to be a hill or a valley, or it can possibly be at the endpoints of the input. Another important theorem is Fermat's theorem. And this is the theorem that says the following. Suppose f has a maximum or minimum at x equals x naught, and f prime exists at x equals x naught, then it turns out that we know what f prime has to be. Does anyone know what f prime has to be? It has to be 0. Turns out if you have a maximum or minimum and your derivative exists at the point, it has to be 0 at the point. There are some important comments. One, the converse is not true. Okay, meaning if you know the derivative is 0, it does not mean it's a max or a min, right? But if you know it's a max or a min, the derivative has to be 0. So f prime equals 0 does not mean max or min. I can give you an example here. Y equals x cubed is an example. Because here my y prime is going to be 3x squared, which is 0 at x equals 0, but it's not a max or min. Right? Y equals x cubed looks like that. The derivative is 0 at that point, but it's neither a max or a min. It's not higher than everyone locally, it's not smaller than everyone locally. Right? So it's very important that you take Fermat's theorem for what it means. It's the order in which you can conclude something matters. Okay, here's another important remark. So it says, if the derivative exists, we kind of know that this has to happen at maximums and minimums, but just because the derivative does not exist actually doesn't mean anything specific, right? So another comment is, we can have maximums or minimums even if f prime does not exist, right? Remember, the derivative is a limit, so limits might not exist. It's possible for f prime to not exist, but we can still attain a maximum or minimum. Can anyone give me an example? Tell me a function and give me a point on that function that's a maximum or a minimum, but the derivative does not exist there.
Wow.
Yeah.
Absolute value of x.
Absolute value of x is an example. We discussed this function before. That's the guy that looks like a v. This point here is clearly a minimum point. It's the absolute and local minimum, but the derivative does not exist there. So it's a nice theorem, but as stated, it's not very useful. But these two counterexamples are kind of useful. One thing this theorem does tell us is that where the derivative is 0 is a very important point of consideration. It doesn't guarantee things, but it's something you should pay attention to. Also, where the derivative does not exist is an important point of consideration, because we can attain maximums and minimums there even though the derivative does not exist. So these two ideas are going to be important ideas for us. They are going to be the things that we want to locate. And we are going to, therefore, make a definition about them. So in terms of calculus and in terms of maximums and minimums, there are 2 points that are of interest to you. Points where the derivative is 0 and points where the derivative does not exist. We will call such points critical points. X naught is called a critical number. If f prime at x naught is 0 or undefined. The point x naught comma f of x naught is called a critical point. So these are critical points. There are 2 points that are very important, as indicated by Fermat's theorem. Where derivative is 0 is going to be important. Where derivative is undefined is going to be important. We'll call these critical points. It's critical! It's critical that we find these. Oh, man. So, it's very critical! Okay. Right, so these points are very critical in terms of maximums and minimums. Okay? They're kind of going to be the places where we look to find the maximums and minimums. So I give you a random function and I see where are the maximums and minimums of this function. You are literally going to look for all the points where the derivative is 0 or it's not defined. And those are the points that you're going to really assess whether they're maximums or minimums. Right? And this is one of the it's a chief use of the derivative to attain maximums and minimums of functions. Like I said, for some functions we can kind of know what they are. For example, parabolas, we know how to find maximums and minimums. Those are just the vertices of the parabolas. But in general, for a general random function, how do you find where the maximum and minimum is? There's no general formula. There's a general procedure though. The procedure is find the derivative and set it equal to 0 undefined. Find all those points and you're going to test them some. So let's look at finding, we're going to talk about finding local maximums and minimums later, and I guess on Friday. But right now let's talk about finding absolute maximums and minimums. There's something called the closed interval method. So this is a method on how to find the absolute max or min of a function on a closed interval. Suppose f of x is continuous on an interval AB, which by the way, the extreme value theorem will guarantee that it has an absolute max or min in this case. I want to say absolute extrema, but that's right here. We'll have to define that later. To find an absolute min, you go through this 3-step process. 1, find all critical points. 2, So that's going to be step one. I give you a random function, it's continuous on some closed interval, I ask you to find the absolute max or min on that interval. First thing you're going to do is you're going to find all the critical points. You're going to find all the points where the derivative is 0 or undefined. 2, you're going to evaluate the function at the endpoints. I.e., find f of a and f of b. 3, compare all the y values. So once you go through this process, you find all the critical points, you find all their y values, you evaluate the function at the endpoints, find those y values, you're going to compare all the y values, and the largest is the absolute max. And the smallest is the absolute min. So step 1 checks for the possibility that a local maximum or minimum is the absolute maximum or minimum. Step 2 checks for the possibility that the absolute max or min occurs at the endpoints at A or B. And 3 is where you're making this assessment. Let's do an example. Let's find the absolute maximum and minimum of x squared on that interval. So 1, we know these points exist because x squared is continuous on this interval. In fact, it's continuous everywhere. It's a polynomial. And you can probably also see what these points are going to be. I mean, this is y equals x squared. We're going from the point from x equals minus 1 to x equals 2. You can kind of already see what the picture looks like, but what if we didn't know the picture? We can still find them through this process. But let's actually go through it. Step 1, you're going to find the critical points. How do you find critical points?
Say the derivative equals 0.
Right, so find y prime. And you're going to set y prime equals 0 or undefined. Right? This would mean that 2x equals 0, so that x equals 0. This, it's always defined, so you can ignore this part. So there's one critical point here. This is the only critical point, well, critical number. I want to find the y value there. So y of 0 is equal to 0 squared, 0. Then you go on to the second step. Check the endpoints. So I'm going to find y of minus 1, which is going to be minus 1 squared, which is 1. I'm going to find y of 2, which is 2 squared, which is 4. In step 3, we're going to compare. So we've found 3 y values that are of interest here. Who's the absolute max? 2. Well, the absolute max is referring to the y value, so you should say 4 is the absolute max. It's also customary to write down, actually express what the input is. So the answer is usually going to be expressed as y of 2 equals 4 is the absolute max. Right, the absolute max is really the y value, but it's people usually indicate the x value that this occurs at.
If it occurs at multiple x points, you have to listen to all.
You have to list them all. Alright, so you might say y of 2 equals y of 7 equals y of 10 equals 4 is the absolute max. So just list all of these points. So you know it attains that multiple times, and these are the x values at which it attains it. And so the absolute min is going to be, of all these y values, you pick the smallest one, which is that one. So you can say y of 0 equals 0 is the absolute min. And that's the end. And we'll stop there. We'll do some more examples next time. We'll pick up with this and do curve sketching also on Friday. On Tuesday we have our test. Huh?
Tuesday?
Yes, Tuesday. It's on video. Come on.
We got YouTube on your website.
I don't know who keeps recording me and posting videos of